Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into Earth's most patient and enduring fire, the radioactive flame that has burned without interruption for over 4 billion years. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. Deep within Earth's core, where pressure crushes atoms and temperatures rival the surface of the sun, a different kind of fire burns. Not the quick yellow flames that dance in hearths or the brief blue tongues that flicker from gas burners, but something far more patient, far more enduring. The radioactive elements scattered throughout Earth's interior have been releasing their energy grain by grain, atom by atom, for longer than life has existed on the surface. This is the flame that never goes out. 4.5 billion years ago, when Earth was still gathering itself from the cosmic dust of the early solar system, uranium atoms were already embedded in the forming rock. Each one carried within its nucleus the potential for transformation, not the violent, sudden change of surface fires, but the slow, inexorable decay that would power the planet's internal engine across geological time. These atoms wait in darkness, some buried 20 miles beneath mountain ranges, others suspended in the molten rock of the deep mantle, each one following its own quiet schedule of atomic dissolution. The uranium buried in granite veins releases its energy with the quiet persistence of falling snow. Each atomic decay releases a tiny burst of heat, barely enough to warm a single grain of sand, yet when multiplied across the entire planet, across billions upon billions of atoms, this becomes the engine that moves continents. The scientific fact seems almost impossibly gentle. Radioactive decay provides roughly half of all the heat flowing from Earth's interior, some 44 trillion watts of continuous power, equivalent to thousands of nuclear reactors running without pause since before the first bacteria learned to photosynthesize. In the deepest parts of the continental crust, where granite bodies stretch for hundreds of miles in every direction, uranium and thorium atoms cluster together in crystal lattices that formed before the atmosphere contained oxygen. These ancient granites hold concentrations of radioactive elements that would have glowed visibly if anyone had been there to see them in Earth's early days. Now they rest in perfect darkness, their radioactive inventory slowly diminishing as each atom fulfills its destiny of decay, releasing heat that will travel upward through miles of stone before warming the surface world. Yet there is something dreamlike in how this process works. The thorium atoms nestled in deep granite wait millions of years between each moment of transformation, then surrender their energy in a flash that lasts less than a microsecond. Like planetary meditation, each element follows its own rhythm of decay. Uranium 238 with its half-life of 4.5 billion years. Thorium 232 waiting even longer at 14 billion years. Potassium 40 moving more quickly through its billion-year cycle. Some uranium atoms present at Earth's formation have already completed their transformation into lead, their energy long since radiated away as heat. Others will not begin their decay process for billions of years to come. The heat these atoms generate moves through rock with the patience of geological time. A single calorie of radioactive warmth might spend 10,000 years migrating from a uranium grain buried in deep granite up through layers of schist and sandstone before finally reaching the surface as a barely detectable temperature increase in a mountain stream. Along the way, this heat drives processes that reshape the planet melting rock into magma, creating the buoyancy differences that drive plate tectonics, powering the convection currents that stir the mantle like an impossibly slow cosmic soup. The mystery that keeps geophysicists awake at night centers on exactly how much of each element lies buried in the unreachable depths of the mantle and core. They measure the heat flowing up through ocean floors and calculate backward, but the Earth keeps its nuclear inventory largely secret. Some models suggest that the core itself contains significant uranium and thorium, their decay contributing to the heat that keeps iron molten at the planet's center. Other theories propose that most radioactive elements concentrated in the crust during Earth's formation, leaving the deep interior heated primarily by the slow cooling of primordial heat. The truth waits in darkness, 2,900 miles below. Beyond the reach of any drill or probe, scientists can calculate that Earth releases about 87 milliwatts of heat per square meter of surface area, roughly equivalent to the energy output of a single LED Christmas light spread across an area the size of a living room. Yet when integrated across the entire planet, this gentle warmth represents more energy than all human civilization has ever used. The radioactive furnace beneath our feet produces more heat in a single day than all the power plants, cars, and factories in the world generate in a year. Only took 4 billion years to put this system online. The irony settles like dust on everything. The planet that harbors life stays warm enough for liquid water to exist because of the same radioactive processes that can prove deadly to living things. Only took 4 billion years for Earth to perfect this balance. The very elements that make nuclear weapons possible have been keeping the planet habitable since before complex molecules learned to replicate themselves. And perhaps most quietly amusing of all, every hot spring that soothes tired muscles, every geothermal vent that warms a winter morning, draws its heat from the same nuclear reactions that governments spend fortunes trying to control and contain. In the deepest ocean trenches, where tectonic plates dive back into the mantle, radioactive elements make their slow journey toward the planet's interior. Water cannot penetrate to the depths where uranium burns, yet the heat it generates finds its way back to the surface through pathways that wind through solid rock like thermal rivers. Some of this heat emerges at mid-ocean ridges, where new seafloor spreads outward at the speed of growing fingernails. Other portions rise beneath continents, warming groundwater and creating the geothermal gradients that make underground mining increasingly difficult with depth. The Earth breathes out this radioactive warmth like a planetary exhale, slow and steady, warming the rock above grain by grain until thermal currents carry it toward the surface in century-long migrations. In laboratories around the world, scientists study tiny samples of deep rock brought up by drilling projects, measuring the trace amounts of helium and other noble gases that radioactive decay has been producing for billions of years. These atoms, trapped in crystal structures since the Archean Eon, tell stories of deep time and patient fire, somewhere far below, in darkness that has never known sunlight. Uranium atoms continue their patient work of splitting apart, keeping the flame alive for another day, another millennium, another geological age. The fire burns without oxygen, without fuel in any conventional sense, sustained only by the fundamental instability built into heavy atomic nuclei at the moment of their birth in ancient stellar cores. This is energy older than the solar system, borrowed from dying stars and repurposed to warm a world where life could slowly learn to exist. The flame never goes out because it was never lit. It simply began burning the moment Earth began to be, and it will continue until the last radioactive atom completes its transformation into something stable and cold. Until then, deep in the planetary dark, the gentle fire burns on. The uranium-238 atom waits in its granite prison with the patience of deep time. embedded in feldspar crystals that formed when the first continents were still taking shape. Each atom carries within its nucleus the accumulated instability of 92 protons and 146 neutrons, a configuration so heavy, so energetically awkward, that it cannot maintain itself forever. The atom exists in a state of perpetual, almost collapse, balanced on the knife edge between stability and transformation, waiting for the quantum moment when it will finally surrender 2 protons and 2 neutrons in a burst of alpha radiation. This waiting is not the anxious anticipation of conscious beings, but something far more profound, the mathematical certainty of radioactive half-life playing out across spans of time that make human civilization appear as brief as a lightning flash. 4.5 billion years, that is how long it takes for half of any collection of uranium-238 atoms to complete their decay. Some atoms will transform within seconds of their birth in ancient stellar cores. Others will wait longer than the universe has existed so far, maintaining their precarious nuclear architecture through ice ages and mass extinctions, through the rise and fall of mountain ranges, through the slow dance of continental drift that has rearranged the planet's surface dozens of times. In the deep granite batholiths that form the cores of mountain ranges, uranium concentrations reach levels that would have made these rocks glow with their own faint light in Earth's early days. The Karelian Shield in northern Europe, formed nearly 3 billion years ago, contains uranium deposits so rich that they once sustained natural nuclear chain reactions, geological reactors that burned for hundreds of thousands of years, consuming uranium fuel and producing radioactive waste products that remain embedded in the rock today. These ancient reactors represent one of the most quietly astonishing discoveries in nuclear geology. Nature achieved controlled nuclear fission 2 billion years before humans learned to split atoms intentionally. The scientific precision of uranium's decay follows laws that seem almost absurdly exact for such a chaotic process. Each uranium-238 atom, when it finally releases its alpha particle, recoils with a specific kinetic energy, 196 million electron volts, precise to the 3rd decimal place. This recoil heat represents the conversion of a tiny amount of nuclear mass into thermal energy. Following Einstein's equation with mathematical perfection, the alpha particle itself, essentially a helium nucleus, travels only about 20 micrometers through solid rock before being absorbed, depositing all of its energy as heat in a volume smaller than a bacterial cell. Yet the poetry lies not in uranium's precision, but in its randomness. No force in the universe can predict which uranium atom will decay next, or when. The process follows statistical laws that describe populations of millions or billions of atoms, but individual atoms remain forever unpredictable. A uranium atom formed in the core of a dying star 5 billion years ago might decay in the next millisecond, or it might continue waiting for another 5 billion years. Each atom carries its own quantum lottery ticket, with odds that never change no matter how long the waiting continues. Deep in the continental crust, where temperatures reach 800 degrees Celsius and pressure squeezes rock into new crystalline forms, uranium atoms continue their patient glow. The heat they generate creates thermal gradients that drive slow convection currents in the solid rock itself, movements so gradual that stone flows like honey, carrying uranium-rich minerals upward over millions of years. Some uranium finds its way into groundwater systems, where it travels through networks of microscopic fractures before being captured again by clay minerals or crystallizing into new ore deposits. The mystery that puzzles geochemists centers on uranium's original abundance in the solar system. Current models suggest that Earth should contain roughly twice as much uranium as geologists have been able to account for. The missing uranium might be hidden in the planet's core, dissolved in the iron-nickel alloy that forms the deepest layer of the Earth. Or it might have been lost during the violent early bombardment period, when asteroid impacts regularly vaporized parts of the planetary surface. Some of Earth's uranium inventory might literally be scattered across space, blown away by cosmic collisions that occurred before the atmosphere became thick enough to retain heavy elements. In uranium mines around the world, where miners extract ore from deposits concentrated by billions of years of geological processes, radiation detectors click constantly as they register the steady stream of alpha particles, beta rays, and gamma radiation produced by uranium's decay chain. Each uranium atom that decays triggers a cascade of further radioactive transformations, daughter isotopes that are themselves unstable, creating a family tree of radioactive elements that eventually terminates in stable lead-206. This decay chain produces 14 different radioactive isotopes, each with its own half-life, its own characteristic radiation signature, its own contribution to the planetary heat budget. The irony of uranium's situation reveals itself in scales both vast and intimate. These atoms, formed in the nuclear furnaces of stars that died before the solar system existed, now provide the steady heat that keeps Earth's interior molten and drives the plate tectonic processes that make complex life possible. Only took 4.5 billion years for stellar death to become planetary life support. The same element that powers nuclear submarines and generates electricity for cities has been quietly heating the planet from within since before oxygen existed in the atmosphere. And, perhaps most gently absurd of all uranium atoms, decay more slowly when they move at high speeds, meaning that uranium ore transported in fast-moving vehicles actually ages more slowly than uranium sitting still in the ground. Following the time dilation effects predicted by special relativity, scientists have calculated that the uranium currently present in Earth's crust and mantle will continue providing significant heat for another billion years or more. But the output is slowly declining as more atoms complete their transformation to lead. Earth's uranium-powered furnace operates on a fuel supply that cannot be replenished. Each decay reduces the total inventory by one atom, and stellar nucleosynthesis occurs too rarely and too far away to replace what is lost. The planet is gradually cooling as its nuclear fuel burns out, though the process occurs so slowly that the sun will likely expand into a red giant and boil away the oceans long before uranium's heat becomes insufficient to drive plate tectonics. Somewhere beneath every footstep, uranium atoms continue their ancient work of self-destruction, each decay adding its microscopic contribution to the thermal pulse that keeps the planet alive. In laboratories and mines, in deep ocean sediments and high mountain granite, in the basement rock beneath cities and farms, uranium-238 maintains its 4-billion-year-old rhythm of patient glow. The atoms wait in their crystal prisons, following quantum laws that guarantee transformation while revealing nothing about timing, burning with a nuclear fire that connects the death of ancient stars to the warmth of living worlds. The uranium burns on, atom by atom, heartbeat by heartbeat, in the eternal patience of radioactive time. In the deeper silence of granite bedrock, where uranium atoms flash and fade in their ancient rhythm, thorium waits with an even greater patience. These atoms, forged in the same stellar crucibles that created uranium, carry 90 protons and between 138 and 142 neutrons, depending on their specific isotope. But thorium-232, the most common form, practices a patience that borders on the geological sublime. Its half-life stretches across 14 billion years, longer than the universe has existed, longer than Earth will survive the sun's eventual expansion into a red giant. Thorium atoms embedded in granite crystals have been waiting since before the Milky Way galaxy settled into its current spiral configuration. Some thorium present in Earth's crust today began their radioactive countdown when the universe was less than half its current age, when the first generation of heavy stars was still forging elements in their nuclear cores. These atoms have witnessed the formation of solar systems, the birth and death of countless worlds, the evolution of life from simple chemistry to conscious beings, and most of them have not yet reached the halfway point of their radioactive lifespan. The concentration of thorium in Earth's continental crust averages about 12 parts per million, 4 times more abundant than uranium, yet contributing roughly equal amounts of heat due to its extraordinarily long half-life. In certain granite formations, particularly those rich in rare earth minerals, thorium concentrations can reach several hundred parts per million. The Conway granite in New Hampshire contains so much thorium that early 20th century geologists could detect its presence using primitive radiation counters, leading to brief speculation about commercial thorium mining before the technical challenges proved overwhelming. Each thorium-232 decay releases 4.28 million electron volts of energy, slightly less than uranium's output, but delivered with the same precise quantum mechanics. The thorium atom emits an alpha particle, 2 protons and 2 neutrons bound together, and recoils in the opposite direction like a microscopic cannon firing an atomic cannonball. The alpha particle travels approximately 15 micrometers through granite before depositing all its kinetic energy as heat in the surrounding crystal matrix. At the scale of atomic decay, this represents a journey across vast distances, thousands of times the diameter of the original thorium nucleus. Yet, thorium's contribution to Earth's heat budget operates through sheer abundance rather than rapid decay. While uranium atoms transform themselves at a relatively brisk pace, thorium atoms wait in their granite prisons with a patience that makes geological time seem hasty. The mathematical precision of this patience follows from quantum mechanics. Each thorium atom has exactly the same probability of decaying in any given moment, regardless of how long it has already waited. An atom that has been stable for 10 billion years has the same chance of decaying in the next second as one that formed yesterday. Deep in the continental shields, the ancient granite cores of continents that have remained stable for billions of years, thorium atoms continue their quiet glow in formations that predate complex life on Earth. The Canadian Shield, parts of which formed nearly 4 billion years ago, contains thorium deposits that have been contributing to the planet's heat budget since before photosynthesis evolved. These thorium atoms have been warming the rock around them through the entire history of life on Earth, providing the steady heat flow that drives groundwater circulation and maintains the temperature gradients necessary for many geological processes. The mystery surrounding thorium centers on its curious scarcity in meteorites and lunar samples compared to its relative abundance in Earth's crust. Current theories suggest that thorium, because of its large atomic size and complex chemistry, concentrated preferentially in the rocky materials that formed Earth's continents rather than being distributed evenly throughout the solar system. This concentration process may have occurred during the violent period of planetary accretion, when repeated impacts and melting events allowed heavy, incompatible elements like thorium to migrate toward Earth's surface layers. Thorium's decay produces a cascade of daughter isotopes even more complex than uranium's decay chain. The thorium-232 decay series includes 12 different radioactive steps, each producing its own characteristic radiation signature. One of the most significant daughters is radon-220, a radioactive gas that can accumulate in underground spaces and contribute to background radiation exposure in buildings constructed over thorium-rich bedrock. This radon gas represents thorium's most direct connection to the surface world in visible evidence of atomic transformations occurring deep in the granite foundation beneath human settlements. In research laboratories around the world, scientists study thorium not only for its role in Earth's heat budget, but also for its potential as a nuclear fuel. Thorium-232 itself is not fissile, but when bombarded with neutrons, it transforms into uranium-233, which can sustain nuclear chain reactions more efficiently than the uranium-235 used in conventional reactors. This transformation represents a kind of atomic alchemy thorium, the patient element that waits billions of years between decay events, can be convinced to change its nuclear behavior entirely when exposed to the right conditions. The irony of thorium's situation encompasses scales both cosmic and intimate. These atoms, born in stellar explosions that occurred before Earth formed, now provide the steady background heat that keeps groundwater liquid in the deep continental crust. Only took 14 billion years for stellar nucleosynthesis to become planetary central heating. Thorium's extraordinary stability makes it nearly immortal by human standards, yet its gradual decay ensures that Earth's continents will eventually cool and cease their geological activity. And perhaps most quietly paradoxical of all thorium, the most patient of radioactive elements, could potentially be engineered to release its energy thousands of times faster than nature intended, transforming eons of stored starlight into electricity for human use. The mathematics of thorium's patience create strange temporal overlaps. Thorium atoms decaying today in granite bedrock began their countdown when the first quasars were lighting up in the early universe. Some thorium atoms present at Earth's formation are only now approaching their halfway point toward decay. Others will continue waiting long after the Sun has exhausted its hydrogen fuel and begun its transformation into a white dwarf star. Thorium connects deep time to deep space, carrying within each atom the memory of stellar death and the promise of planetary warmth extending into an almost unimaginably distant future. In the laboratory, thorium samples must be stored with careful attention to radiation safety protocols, despite the element's extremely slow decay rate. Over geological time, even thorium's gentle radioactivity accumulates significant radiation exposure. Granite quarry workers and stonemasons working with thorium-rich rock face occupational health considerations that reflect billions of years of accumulated radioactive decay. The atoms glow softly in their crystal prisons, each decay event representing the culmination of a wait that began before complex life evolved on Earth. Somewhere in the granite foundations of every continent, thorium atoms continue their 14 billion year meditation on nuclear physics. They wait in perfect darkness, following quantum laws that make their individual behavior unpredictable, while ensuring their collective contribution to planetary heat remains mathematically precise. The thorium whispers through deep time, patient as stone, steady as starlight, burning with a nuclear flame that connects the first moments after the Big Bang to the quiet warmth flowing upward through granite bedrock today. The whisper continues, atom by atom, eon by eon, in the endless patience of thorium time. In the vast reaches of the mantle, where rock flows like thick honey under pressures that would crush surface materials into powder, potassium-40 atoms tick away their radioactive countdown with the steady persistence of a planetary heartbeat. These atoms, dispersed throughout the silicate minerals that form the bulk of Earth's interior, follow a different rhythm than their uranium and thorium companions. With a half-life of 25 billion years, potassium-40 operates on a timescale that bridges the gap between thorium's geological patience and the more urgent decay of shorter-lived isotopes. Potassium-40 represents only 0.0% of all potassium atoms in nature, yet this tiny fraction carries enormous significance for planetary energetics. The vast majority of potassium exists as stable potassium-39, chemically identical but lacking the nuclear instability that makes potassium-40 radioactive. These stable atoms serve as silent witnesses to their radioactive siblings' transformations, embedded in the same mineral structures but contributing no heat to the planetary engine. Only the unstable isotope participates in Earth's nuclear fire, transforming itself through two different decay pathways with the reliability of atomic clockwork. Most potassium-40 atoms, roughly 89%, undergo beta- decay, transforming a neutron into a proton and emitting an electron along with an electron antineutrino. This process converts the potassium atom into calcium-40, releasing 1.31 million electron volts of energy in the form of kinetic energy carried by the ejected electron. The remaining 11% of potassium-40 atoms follow a more exotic path called electron capture, in which the nucleus absorbs one of its own orbital electrons and converts a proton into a neutron, transforming the atom into argon-40 while releasing a neutrino and characteristic X-rays. The ubiquity of potassium in rock-forming minerals means that potassium-40's gentle pulse reaches every corner of Earth's interior. Feldspar crystals in granite contain potassium concentrations that can exceed 10% by weight, while the olivine and pyroxene minerals of the mantle typically hold smaller but still significant amounts. Even the iron-nickel alloy of Earth's core may contain trace amounts of potassium, though the extreme conditions at such depths make the behavior of radioactive elements largely theoretical. In the deep mantle, where temperatures reach 3,000 degrees Celsius and pressures exceed those found at the bottom of the deepest ocean trenches by a factor of 1,000,000. Potassium-40 atoms continue their decay with undiminished regularity. The intense conditions alter the physical properties of minerals. Diamond becomes stable. Silicate structures reorganize into exotic crystal forms, but radioactive half-lives remain unchanged. Nuclear processes operate according to laws that transcend the crushing forces and searing heat of planetary interiors. Each potassium-40 decay event releases its energy into the surrounding mineral matrix as heat. But the pathway from atomic nucleus to bulk thermal energy involves complex interactions with the crystal structure of the host rock. The high-energy electron produced by beta decay travels several tens of micrometers through solid silicate before being absorbed, depositing its kinetic energy as thermal vibrations in the crystal lattice. These thermal vibrations, phonons, in the language of solid-state physics, represent the conversion of nuclear binding energy into the random motion of atoms that we perceive as heat. The distribution of potassium throughout Earth's interior follows patterns established during the planet's formation and early differentiation. Unlike uranium and thorium, which concentrate preferentially in granite and other evolved crustal rocks, potassium behaves as a moderately incompatible element during mantle melting. This means that potassium tends to partition into magmas during partial melting events, gradually migrating from the deep mantle toward the surface over geological time. The process operates like a slow distillation, concentrating potassium-40 in the upper portions of the Earth while leaving the deep mantle relatively depleted. The mystery that intrigues geophysicists involves the total inventory of potassium in Earth's core. Some models suggest that significant amounts of potassium dissolved in the iron-nickel alloy during the planet's formation, when metal and silicate phases were in equilibrium at extremely high temperatures. If correct, this would mean that potassium-40 decay contributes to heating the core itself, potentially influencing the generation of Earth's magnetic field through its effects on core convection. Other models propose that potassium remained almost entirely in the silicate portions of the planet, making core heating primarily the result of cooling from primordial accretional heat. Laboratory experiments designed to resolve this question face the fundamental challenge of reproducing core conditions in the laboratory. The pressures and temperatures at Earth's center exceed anything that can be sustained for long periods in experimental apparatus, forcing scientists to extrapolate from measurements made under less extreme conditions. Meanwhile, the deepest drill holes barely scratch the surface of the continental crust, leaving the vast majority of Earth's potassium-40 inventory accessible only through indirect seismic and geochemical inference. The irony of potassium-40's role in planetary heating extends across multiple scales of observation. These atoms, essential components of common rock-forming minerals, generate heat through the same nuclear processes that power hydrogen bombs, yet do so with such gentle efficiency that the warmth they produce supports rather than destroys the complex chemistry of life. Only took 1 billion years for stellar nucleosynthesis to perfect this nuclear thermostat. Potassium-40's moderate half-life means that Earth has lost roughly half of its original inventory since formation, making the planet's early thermal history significantly more energetic than its current state, and, perhaps most subtly paradoxical of all potassium, an element so chemically reactive that it bursts into flame when exposed to water, exists in vast quantities in the hottest, most energetic regions of the planet's interior without undergoing any chemical reactions at all. The heartbeat of potassium-40 resonates through Earth's entire structure. In the oceanic crust, where basaltic rocks contain modest but measurable potassium concentrations, radioactive decay contributes to the heat flow measured at mid-ocean ridges. In the continental crust, where granitic rocks can contain several percent potassium by weight, the cumulative heat production from potassium-40 decay helps drive the deep groundwater circulation systems that create hot springs and geothermal reservoirs. In the mantle, potassium-40's steady energy release contributes to the convection currents that move tectonic plates and recycle surface materials back into the planetary interior. Geochemists studying volcanic rocks can track the migration of potassium through the mantle by analyzing the ratios of potassium-40 to its decay product, argon-40. Because argon is a noble gas that does not readily incorporate into mineral structures, it tends to escape from rocks during melting events, resetting the radioactive clock and allowing scientists to date volcanic eruptions with remarkable precision. This dating technique, known as potassium-argon geochronology, has revealed the timing of major volcanic events extending back hundreds of millions of years. The pulse continues in laboratories around the world, where sensitive radiation detectors register the steady emission of electrons and gamma rays from potassium-40 in ordinary rock samples. Museum specimens of granite and basalt click quietly in their display cases as potassium atoms complete billion-year journeys from nuclear instability to stable decay products. The sound represents the culmination of atomic processes that began when the solar nebula was still condensing from interstellar dust. Each decay event marking another heartbeat in the slow rhythm that has powered plate tectonics since Earth began cooling from its initial molten state. Somewhere in the flowing rock of the upper mantle, in the crystal matrices of deep crustal granite, in the mineral assemblages of metamorphic terrains formed billions of years ago, potassium-40 atoms continue their patient countdown. They tick away the moments of geological time with quantum precision, each decay contributing its small pulse of heat to the thermal engine that drives continental drift, mountain building, and the circulation of elements between Earth's surface and interior. The heartbeat echoes through deep time, steady and reliable, connecting the nuclear physics of stellar interiors to the gentle warmth that flows upward through rock formations older than complex life. The pulse continues, heartbeat by heartbeat, decay by decay, in the eternal rhythm of potassium time. The heat generated by radioactive decay in Earth's deepest places begins its upward journey through rock with the patience of thermal diffusion, moving grain by grain through crystal structures that have never known sunlight. This is not the rapid convection of boiling water or the swift conduction through metal, but something far more gradual, the slow migration of kinetic energy through solid rock, where individual phonons carry their thermal cargo across distances measured in atomic diameters, one vibrational step at a time. Deep in the mantle, where olivine crystals the size of building blocks flow like putty under immense pressure, heat released by potassium. 40 decay begins its 1,000-mile ascent toward the surface. Each quantum of thermal energy must navigate through crystalline structures where atoms are locked in rigid geometric patterns, yet paradoxically able to flow over geological time. The heat moves through these mineral assemblages like a message passed through an enormous crowd, each atom receiving thermal vibrations from its neighbors and passing them along to the next layer of the crystal lattice. The journey begins at the scale of individual atomic nuclei. When a uranium-238 atom undergoes alpha decay 20 miles beneath a mountain range, the 4 to 196 million electron volts of released energy initially exists as the kinetic energy of recoiling nuclear fragments, within microseconds. This kinetic energy has been converted to thermal vibrations in the surrounding granite matrix. The alpha particle, essentially a helium nucleus, travels approximately 20 micrometers through solid rock before coming to rest, depositing its energy as heat in a volume smaller than most bacterial cells. From this microscopic beginning, the thermal energy spreads outward through the granite like ripples in a three-dimensional pond. But, unlike ripples in water, which travel at the speed of sound, thermal energy in rock moves with the deliberate pace of diffusion. Individual phonons, quantized packets of vibrational energy, hop from atom to atom at rates determined by the crystal structure and temperature of the host rock. In granite, at typical crustal temperatures, thermal diffusivity allows heat to travel roughly 1 meter per 1,000 years. The mathematics of this process follow Fourier's law of heat conduction with remarkable precision. Despite the complex mineral assemblages through which the heat must travel, granite contains multiple mineral phases: quartz, feldspar, mica, each with different thermal properties. Yet the bulk behavior averages out to predictable heat flow patterns. Scientists can calculate that a calorie of heat generated by uranium decay in deep continental crust will require approximately 10,000 years to reach the surface, assuming a direct vertical path through 20 kilometers of granite. Yet the actual pathways prove far more complex than simple vertical conduction. The continental crust contains networks of fractures, fault zones, and areas of altered rock that create preferential pathways for heat flow. Groundwater circulation systems can dramatically accelerate heat transport in some regions while creating thermal barriers in others. Where hot springs emerge at the surface, they represent the culmination of thermal journeys that may have begun millions of years ago in radioactive granite bodies far below. The mystery that fascinates geophysicists centers on the apparent efficiency of heat transport in Earth's interior compared to simple conductive models. Measurements of surface heat flow often exceed what would be expected from conduction alone, suggesting that convective processes, the physical movement of heated rock, play crucial roles in transporting radioactive heat from source regions to the surface. In the mantle, solid rock convection operates over time scales of millions of years, creating circulation patterns that carry heat from the deep interior to shallow depths far more rapidly than conduction alone could achieve. Laboratory experiments reveal the intricate details of heat transport through rock-forming minerals. Scientists use laser heating systems to create temperature gradients across tiny mineral samples, then measure how thermal energy propagates through different crystal structures. Olivine, the dominant mineral in Earth's upper mantle, conducts heat more efficiently along certain crystallographic axes than others, creating anisotropic thermal properties that influence the patterns of heat flow on continental scales. Quartz crystals show similar directional preferences, conducting heat more readily parallel to their hexagonal crystal faces than perpendicular to them. The influence of pressure on thermal conductivity adds another layer of complexity to heat transport calculations. As radioactive heat travels upward from deep source regions, it encounters decreasing pressure conditions that alter the thermal properties of the rock through which it moves. Minerals that are excellent thermal conductors under deep crustal conditions may become less efficient heat transporters near the surface, where reduced pressure allows crystal structures to expand and thermal pathways to become less direct. Temperature itself affects the efficiency of heat conduction through rock. The relationship follows a roughly inverse correlation. Hotter rocks tend to be less effective thermal conductors than cooler ones. This creates a self-regulating feedback system. Regions of high heat production tend to develop thermal properties that partially limit their own heat transport efficiency, preventing the development of extreme temperature gradients that might destabilize the crystal structures involved. The irony of radioactive heat transport reveals itself across scales both microscopic and continental. Individual atoms vibrating at frequencies of trillions of cycles per second carry thermal energy through crystals where nothing appears to move at human timescales, yet the cumulative effect drives geological processes visible from space. Only took 4 billion years for quantum vibrations to become continental drift. Heat generated by atomic processes occurring in volumes smaller than virus particles ultimately powers the formation of mountain ranges that stretch across thousands of miles. And perhaps most quietly counterintuitive of all, the fastest heat transport in Earth's interior occurs through the physical movement of solid rock. While the presence of liquid water, an excellent conductor in surface environments, can actually impede heat flow in some deep crustal settings where hydrothermal alteration creates thermally insulating clay minerals. Thermal infrared satellites orbiting Earth can detect the subtle temperature variations that represent the surface expression of radioactive heat sources buried miles below. These measurements reveal the signature of deep granite batholiths, uranium-rich zones in the continental crust, and areas where thermal springs indicate efficient heat transport from depth. The satellite data create maps of invisible fire, the surface expression of nuclear reactions occurring in permanent darkness far below. In research laboratories, scientists recreate the conditions of deep heat transport using high-pressure apparatus that can simulate the temperature and pressure conditions of the lower continental crust. These experiments reveal that heat transport through rock becomes increasingly efficient at higher pressures and temperatures, explaining why the deep continental crust can effectively channel radioactive heat toward the surface despite being composed entirely of solid mineral assemblages. The journey continues in underground mines and deep boreholes, where geologists measure temperature gradients that reflect the upward flow of radioactive heat. The Kola superdeep borehole in Russia, which penetrated more than 12 kilometers into the continental crust, revealed temperature increases that closely match theoretical predictions based on radioactive heat production in granite. Every meter of depth represents another step in the 1,000-mile thermal journey from radioactive source to surface expression. Somewhere in the crystal matrices of deep crustal rocks, in the flowing mineral assemblages of the upper mantle, in the networks of microscopic fractures that honeycomb the continental foundation, thermal energy released by radioactive decay continues its patient ascent toward the surface world. The heat rises through stone with quantum precision, each phonon carrying its microscopic cargo of nuclear energy through crystalline highways that connect the atomic scale to the planetary scale, the nuclear fire below to the gentle warmth above. The heat rises through stone, phonon by phonon, crystal by crystal, in the endless patience of thermal time. In the vast circulating mills of the mantle, where rock flows with the viscosity of cold honey and temperatures reach those of steel furnaces, radioactive heat drives convection currents that have been stirring Earth's interior for over 4 billion years. These are not the rapid, turbulent currents of boiling water, but something far more majestic circulation patterns that complete a single cycle over tens of millions of years, carrying heat and matter through vertical distances of nearly 3,000 kilometers with the inexorable patience of geological time. The mantle exists in a state that challenges human intuition about the behavior of solid matter. At the pressures and temperatures that prevail beneath the continental crust, rock maintains its crystalline structure while simultaneously flowing like an extremely viscous fluid. Olivine crystals the size of sand grains creep past each other over millennia, their atomic bonds breaking and reforming in response to the immense stresses generated by thermal expansion and gravitational forces. The entire mantle participates in this slow dance, stirred by the heat released from radioactive decay and the cooling of primordial thermal energy trapped since Earth's formation. Convection cells in the mantle organize themselves into patterns that span continents. Hot rock, heated by the steady output of radioactive decay in uranium-rich regions, becomes slightly less dense than the surrounding material and begins to rise. This ascending rock follows pathways that may extend from the core mantle boundary to depths of just a few hundred kilometers below the surface, carrying with it the thermal signature of nuclear reactions occurring in the deep interior. As this material rises, cooler rock from higher levels descends to take its place, creating circulation loops that transport both heat and chemical components throughout Earth's interior. The driving force behind these circulation patterns stems from the fundamental physics of thermal expansion. When radioactive decay heats a volume of mantle rock, that rock expands slightly, becoming less dense than its surroundings. The resulting buoyancy forces, though minuscule compared to the enormous pressure at mantle depths, prove sufficient to drive convection when integrated over the vast volumes and extended time periods characteristic of geological processes. A temperature difference of just a few degrees between adjacent regions of the mantle can generate convection currents that persist for hundreds of millions of years. The mathematics of mantle convection involve equations that describe the complex interplay between thermal diffusion, viscous flow, and gravitational forces acting on materials with temperature-dependent physical properties. The Rayleigh number, a dimensionless parameter that characterizes the vigor of thermal convection, exceeds the critical threshold for convective instability in Earth's mantle by several orders of magnitude. This means that the mantle not only can convect, but must convect, driven by the relentless input of radioactive heat from uranium, thorium, and potassium decay. Seismologists studying earthquake waves that travel through the mantle have revealed the three-dimensional structure of these convection patterns. Regions of hot, ascending rock appear as areas of reduced seismic velocity, while zones of cold, descending materials show up as areas where earthquake waves travel more rapidly. These tomographic images reveal convection cells with complex, ever-changing geometries, rising plumes beneath volcanic hotspots, descending sheets of cold oceanic lithosphere, and broad upwelling zones beneath mid-ocean ridge systems. The mystery surrounding mantle convection centers on the relationship between different scales of circulation. Large-scale convection cells that span the entire depth of the mantle operate simultaneously with smaller-scale circulation patterns confined to the upper few hundred kilometers. The interaction between these different scales of convection remains one of the most challenging problems in geodynamics, requiring computer models that can simulate fluid flow across length scales ranging from kilometers to thousands of kilometers and time scales from thousands to hundreds of millions of years. Laboratory experiments designed to understand mantle convection use sophisticated apparatus to recreate the essential physics of thermal convection in high-viscosity fluids. Scientists heat containers of corn syrup, glycerin, or other viscous materials from below and observe the formation of convection cells that scale, according to the principles of fluid dynamics, to the much larger circulation patterns in Earth's mantle. These experiments reveal that convection in high-viscosity fluids tends to organize itself into relatively stable, long-lived circulation cells rather than the chaotic turbulence characteristic of low-viscosity convection. The influence of radioactive heating on mantle convection extends beyond simple thermal driving forces. The distribution of uranium, thorium, and potassium throughout the mantle affects not only the temperature field, but also the chemical evolution of Earth's interior. Radioactive elements tend to be incompatible with the major mantle minerals, meaning they preferentially partition into liquid phases during melting events. This creates a feedback system where radioactive heating promotes melting, which concentrates radioactive elements in the resulting magmas, which increases the heat production in crustal rocks formed from those magmas. The timescales of mantle convection create temporal overlaps that span the entire history of Earth. Convection cells that began forming during the Archean Eon, when the atmosphere contained no oxygen and life consisted entirely of simple bacteria, may still be active today, carrying with them chemical signatures that record the evolution of Earth's interior over billions of years. Meanwhile, new convection patterns continuously develop in response to changing thermal and chemical conditions, ensuring that the mantle remains in a state of perpetual, slow-motion turbulence. The irony of mantle convection encompasses scales both microscopic and planetary. Individual mineral grains flow past each other at rates slower than the growth of human fingernails. Yet, the cumulative motion drives tectonic processes that can thrust mountain ranges skyward at rates visible within human lifetimes. Only took 4 billion years for atomic vibrations to become continental collision. The same convection currents that transport radioactive heat away from deep source regions also bring fresh mantle material into contact with those heat sources, ensuring that the nuclear fire continues to find new fuel for combustion. And perhaps most elegantly paradoxical of all the mantle convects, precisely because it cannot convect efficiently, with high viscosity creating the temperature gradients necessary to sustain circulation while simultaneously limiting the vigor of that circulation. Computer models of mantle convection require some of the most powerful supercomputers in the world to simulate the complex interactions between thermal, chemical, and mechanical processes operating over geological timescales. These models suggest that radioactive heating has been the dominant driving force for mantle convection throughout most of Earth's history, though the vigor of convection has gradually decreased as radioactive elements have decayed and the total heat production has declined. Early in Earth's history, when uranium and thorium concentrations were significantly higher, mantle convection may have been vigorous enough to completely overturn the planet's interior every few 100 million years. The dance continues in three-dimensional patterns of rising and falling rock that connect the deepest parts of the mantle to the shallow regions where magma generation begins. Hot, radioactive heat rises through convection cells that may extend from the core mantle boundary to depths of just a few 100 kilometers below the continents. Along the way, this ascending material carries chemical traces that record the composition of the deep mantle, the history of core-mantle interaction, and the evolution of radioactive element distributions over billions of years. Somewhere in the flowing rock of the upper mantle, in the broad upwelling zones beneath mid-ocean ridges, in the narrow plumes that rise beneath volcanic hotspots, Convection currents driven by radioactive decay continue their ancient circulation patterns. They stir the planetary interior with the patient efficiency of geological time, mixing heat and matter across vertical distances that span most of Earth's radius, connecting the nuclear fire of the deep interior to the tectonic processes that shape the surface world. The mantle dances on, cell by cell, circulation by circulation, in the endless patience of convection time. At the boundaries between continents, where the seafloor spreads apart like an impossibly slow zipper opening, radioactive heat provides the thermal engine that drives one of geology's most elegant and persistent processes. Along the mid-ocean ridge systems that snake through every ocean basin like the seams of a baseball, rising mantle material heated by billions of years of nuclear decay emerges to create new oceanic crust at rates that can be measured with satellite precision, yet require human lifetimes to become visible to the naked eye. The East Pacific Rise, stretching along the eastern margin of the Pacific Ocean, represents one of Earth's most active spreading centers. Here, mantle rock heated by the steady output of potassium, 40 uranium-238, and thorium-232 decay rises from depths of several hundred kilometers, partially melting as it ascends and decompresses. The resulting basaltic magma fills the gap created by the diverging oceanic plates, solidifying to form new seafloor that immediately begins its journey away from the ridge axis at rates of several centimeters per year, roughly equivalent to the speed of growing fingernails. This spreading process operates with mechanical precision that reflects the fundamental physics of thermal expansion and gravitational potential energy. As radioactive heat warms the mantle beneath mid-ocean ridges, the heated rock expands and becomes less dense than its surroundings. This density difference creates buoyancy forces that drive the heated material upward, forming broad zones of mantle upwelling that can extend hundreds of kilometers on either side of the ridge axis. The rising mantle rock carries with it not only heat, but also the chemical signature of deep radioactive processes, including elevated concentrations of incompatible elements that have been concentrated by billions of years of partial melting events. The geometry of seafloor spreading creates a natural conveyor belt system that transports radioactive heat from the mantle to the surface more efficiently than conduction through continental crust. Fresh basaltic rock erupted at mid-ocean ridges contains measurable concentrations of uranium, thorium, and potassium inherited from its mantle source, along with the radiogenic daughter products that record the age and thermal history of the deep interior. As this new oceanic crust moves away from the ridge axis, it carries this radioactive inventory with it, creating a moving archive of mantle composition that spans millions of years of Earth history. The cooling of newly formed oceanic crust follows predictable mathematical relationships that allow geophysicists to calculate heat flow patterns with remarkable accuracy. The plate model of oceanic cooling predicts that heat flow should decrease as the square root of seafloor age, a relationship confirmed by thousands of heat flow measurements collected from research vessels over the past several decades. This cooling process represents the gradual loss of both radioactive heat inherited from the mantle and thermal energy acquired during the melting and eruption process at the ridge axis. Hydrothermal circulation systems develop wherever seawater penetrates into hot, newly formed oceanic crust. These circulation cells, driven by the temperature contrast between cold seawater and hot basaltic rock, create efficient heat transfer mechanisms that can extract thermal energy from the oceanic crust much more rapidly than conductive cooling alone. Black smoke events and other hydrothermal features represent the surface expression of these deep circulation systems, releasing heat that originated as radioactive decay in mantle source regions hundreds of kilometers below the seafloor. The mystery surrounding mid-ocean ridge processes centers on the three-dimensional structure of mantle flow beneath spreading centers. While the basic physics of seafloor spreading is well understood, the detailed patterns of mantle upwelling, the role of compositional heterogeneities in the mantle source, and the mechanisms that focus melting beneath ridge axes remain active areas of research. Seismic tomography studies reveal complex patterns of mantle flow that suggest spreading centers interact with deeper mantle structures, possibly including plumes of hot material rising from the core mantle boundary. Laboratory experiments designed to understand ridge processes use high-temperature furnaces to melt rock samples under controlled conditions that approximate mantle melting beneath mid-ocean ridges. These experiments reveal that the fraction of mantle rock that melts during upwelling depends critically on temperature, pressure, and the presence of volatile components like water and carbon dioxide. Small changes in the thermal structure of upwelling mantle, potentially related to variations in radioactive heat production, can significantly affect the volume and composition of magmas produced at spreading centers. The chemical signature of radioactive processes appears throughout the oceanic crust in the form of trace element patterns and isotopic ratios that record the history of uranium, thorium, and potassium in mantle source regions. Basaltic rocks collected from mid-ocean ridges show systematic variations in radiogenic isotope ratios that reflect the time-integrated effects of radioactive decay in their mantle sources. These isotopic signatures provide windows into processes occurring at depths and over time scales that are otherwise inaccessible to direct observation. Transform faults. The fracture zones that offset ridge segments and accommodate the geometry of spreading on a spherical surface create additional pathways for radioactive heat to reach the seafloor. Along these fault zones, deep-seated fractures may allow mantle-derived fluids and melts to ascend more directly to the surface, bypassing the normal processes of magma chamber storage and fractionation that occur beneath ridge axes. Some transform faults show evidence of serpentinization reactions, where seawater reacts with mantle peridotite to create hydrated mineral assemblages that can transport heat and chemical components from deep mantle sources. The irony of seafloor spreading encompasses temporal and spatial scales that span the entire ocean basins. The same radioactive processes that operate over billion-year timescales drive tectonic processes that create new oceanic crust every few million years, ensuring that no oceanic crust older than about 200 million years remains at Earth's surface. Only took 4 billion years for stellar nucleosynthesis to become oceanic recycling. The heat that drives seafloor spreading ultimately derives from nuclear reactions occurring in mantle source regions that may never directly interact with surface processes. Yet the products of those reactions become incorporated into oceanic crust that covers more than 2/3 of Earth's surface. And perhaps most geometrically elegant of all the linear spreading centers that appear as simple cracks in the seafloor when viewed from above actually represent the surface expression of three-dimensional mantle flow patterns that extend hundreds of kilometers into the planetary interior. Magnetic anomaly patterns preserved in oceanic crust provide an independent record of seafloor spreading rates extending back more than 100 million years. These patterns, created by the alternating polarity of Earth's magnetic field as it became locked into cooling basaltic rocks, reveal that spreading rates have remained remarkably constant over geological time scales. This consistency suggests that the radioactive heat sources driving mantle convection and seafloor spreading have maintained relatively stable output over periods much longer than human civilization. Drilling projects designed to penetrate through the entire thickness of oceanic crust have revealed the detailed structure of the layer cake created by seafloor spreading processes. The upper portion consists of pillow basalts erupted directly onto the seafloor, underlain by a zone of vertical basaltic dikes that fed the surface eruptions, and finally, a lower layer of gabbroic rocks that crystallize slowly in magma chambers beneath the ridge axis. Each layer preserves the chemical and thermal signature of the radioactive heat sources that drove its formation, creating a three-dimensional archive of deep Earth processes. The spreading continues along 60,000 kilometers of mid-ocean ridge systems that encircle the globe like the seams of a tennis ball. Each segment driven by the patient heat of radioactive decay in mantle source regions far below. Magma chambers beneath the ridges serve as temporary storage reservoirs for melts generated by decompression of upwelling mantle, while hydrothermal circulation systems extract and redistribute the heat that powers these remarkable geological engines. Somewhere beneath every mid-ocean ridge, mantle rock heated by 4 billion years of nuclear decay rises toward the surface, partially melts, and erupts to create new sea floor that immediately begins its journey toward distant subduction zones. The process connects the nuclear fire of the deep mantle to the creation of new oceanic lithosphere, the cycling of chemical elements between Earth's interior and surface, and the slow but inexorable drift of continents across the planetary surface. The plates drift apart, ridge by ridge, spreading center by spreading center in the endless patience of tectonic time. Through volcanic vents scattered across the planet's surface, the accumulated heat of radioactive decay finds its most dramatic expression as magma chambers deep beneath Earth's crust release their molten contents in eruptions that can be seen from space. These are the breathing holes of the planetary furnace, where nuclear fire that has been building for millions of years in granite batholiths and mantle source regions finally breaks through to the surface world in displays of molten rock that connect the atomic scale to the human scale with startling immediacy. Mount Vesuvius, sleeping quietly above the Bay of Naples, contains within its magma chamber a molten inventory of radioactive elements that have been concentrated by millions of years of crustal melting processes. The potassium-rich volcanic rocks that form the mountain slopes carry elevated concentrations of potassium-40, uranium-238, and thorium-232 legacy signatures of the deep crustal melting that feeds the volcano's periodic eruptions. Each atom of potassium-40 that decays in the magma chamber contributes its 1.31 million electron volts of energy to the thermal budget that keeps the system molten and potentially explosive. The formation of magma deep beneath volcanic systems represents one of geology's most efficient mechanisms for concentrating and transporting radioactive heat from source regions to the surface. When uranium-rich granite undergoes partial melting at depths of 20 to 30 kilometers, the resulting magmas become enriched in incompatible elements, those atomic species that prefer to dissolve in liquid rather than remain in solid mineral structures. Uranium, thorium, and potassium all behave as incompatible elements during most melting processes, meaning that even small degrees of partial melting can create magmas with radioactive element concentrations several times higher than their source rocks. These enriched magmas rise through the continental crust following pathways of least resistance fracture zones, fault systems, and areas where the overlying rock has been weakened by previous intrusive events. The ascent process can take thousands of years for magmas rising from deep crustal source regions, during which time radioactive decay continues to add heat to the system. A single cubic meter of granite-derived magma may contain billions of uranium-238 atoms undergoing decay during the magma's journey to the surface, each decay event contributing to the thermal energy that maintains the magma in its molten state. Volcanic gas emissions provide direct evidence of radioactive processes occurring in deep magma chambers. Radon-222, a radioactive gas produced by the decay of uranium-238, can be detected in volcanic fumaroles and gas vents, indicating the presence of uranium-rich source regions at depth. The concentration of radon in volcanic gases often increases prior to eruptions, suggesting that changes in the magma chamber's thermal or physical structure can affect the transport of radioactive decay products from depth to surface. The timing of volcanic eruptions reflects complex feedback relationships between radioactive heat production, magma chamber dynamics, and crustal stress fields. Computer models suggest that steady radioactive heating can gradually increase the temperature and pressure within magma chambers, eventually reaching critical thresholds where eruption becomes inevitable. The process operates like a geological pressure cooker, with radioactive decay providing the steady heat input that drives the system toward instability over timescales ranging from decades to centuries. Large igneous provinces, vast volcanic fields that can cover areas comparable to entire continents, represent extreme examples of radioactive heat accumulation and release. The Siberian traps, formed around 252 million years ago during the Permian-Triassic boundary, may have been triggered by the arrival of a mantle plume enriched in radioactive elements at the base of the continental crust. The resulting volcanic activity released enormous volumes of basaltic magma onto the surface, along with climate-altering gases that contributed to one of the most severe mass extinction events in Earth's history. The mystery surrounding the relationship between radioactive heating and volcanic activity centers on the role of crustal architecture in focusing heat and magma transport. Some of the world's most active volcanic systems occur in regions where the continental crust contains unusually high concentrations of uranium and thorium, suggesting that radioactive heating may play a direct role in sustaining long-lived magmatic activity. Other volcanic systems show little correlation between crustal radioactivity and eruptive vigor, indicating that mantle-derived heat sources dominate the thermal budget in those settings. Laboratory studies of volcanic rocks reveal the detailed pathways through which radioactive elements move from deep source regions to surface eruption sites. Mass spectrometer analysis of individual mineral grains can detect the microscopic inclusions of uranium and thorium, bearing accessory minerals that record the thermal history of magma chambers. These studies show that radioactive elements often concentrate in the latest crystallizing phases of magmatic systems, creating radioactive hotspots within solidified volcanic rocks that continue to generate heat long after the eruption has ended. The global distribution of volcanic activity shows statistical correlations with the underlying distribution of radioactive elements in the continental crust. Volcanic fields in regions with high crustal uranium and thorium concentrations tend to produce more silicic, explosive eruptions, while volcanic systems in areas with lower radioactive element abundances more commonly produce mafic, effusive eruptions. This pattern suggests that radioactive heating influences not only the frequency of volcanic activity, but also the style and composition of eruptions. Geothermal energy systems associated with volcanic regions harness the residual heat from radioactive decay in cooling magma bodies. The Geysers geothermal field in California, Yellowstone's hydrothermal features, and Iceland's geothermal power plants all tap into heat sources that ultimately derive from radioactive processes in deep crustal or mantle source regions. These systems demonstrate how the patient nuclear fire burning in Earth's interior can be captured and converted to human useful energy through the intermediary processes of magma generation and hydrothermal circulation. The irony of volcanic systems encompasses both their destructive power and their role in concentrating radioactive elements at Earth's surface. The same nuclear processes that power volcanic eruptions also create the geochemical conditions necessary for forming high-grade uranium ore deposits. As magmatic and hydrothermal processes concentrate uranium from average crustal abundances of a few parts per million to ore-grade concentrations exceeding several percent. Only took 4 billion years for stellar nucleosynthesis to become uranium mining. Volcanic eruptions that can devastate human settlements also serve as efficient mechanisms for transporting essential trace elements, including radioactive species, from deep crustal reservoirs to surface environments where they become incorporated into soils and ecosystems. And perhaps most paradoxically of all the radioactive elements that make volcanic systems potentially hazardous to human health, also provide much of the energy necessary to drive the plate tectonic processes that create the volcanic arcs where most of humanity's population centers have developed. Volcanic monitoring networks around the world use sensitive instruments to detect the subtle changes in heat flow, gas composition, and seismic activity that may herald changes in deep magma chamber behavior. Many of these monitoring techniques indirectly measure the effects of radioactive heating, including the temperature changes produced by varying rates of radioactive decay in magma chambers and the emission patterns of radioactive gases that escape from volcanic vents. The breath continues to escape from thousands of volcanic systems scattered across the planet's surface, each one representing a pathway for radioactive heat to travel from deep source regions to the atmosphere and surface environment. Fumaroles steam quietly on volcanic slopes. Hot springs emerge where magmatic heat intersects groundwater systems, and occasional eruptions release the accumulated energy of millions of years of radioactive decay in spectacular displays of geological power. Somewhere beneath every active volcano, in magma chambers that may extend for miles beneath the surface, radioactive elements continue their ancient work of nuclear transformation while simultaneously providing the heat necessary to maintain molten rock at temperatures exceeding 1,000 degrees Celsius. The volcanic breath connects the nuclear fire of the deep earth to the surface world through pathways that have remained active for billions of years, ensuring that the patient energy of radioactive decay continues to find expression in the dynamic processes that shape the planetary surface. The volcanic breath escapes, vent by vent, eruption by eruption, in the endless patience of magmatic time. In the vast granite bodies that form the crystalline foundations of continents, uranium and thorium atoms find themselves locked within mineral structures that serve as both prison and battery, holding these radioactive elements in place for billions of years while their steady decay provides the thermal energy that warms the deep continental crust. These granite plutons, some extending for hundreds of miles beneath mountain ranges and cratons, represent Earth's most concentrated repositories of nuclear fuel geological storage systems that have been generating heat continuously since before complex life evolved in the oceans. The Sierra Nevada batholith, stretching along 400 miles of California's eastern spine, contains granite intrusions that crystallized between 90 and 200 million years ago, yet continue to release heat from uranium and thorium decay at measurable rates today. Within the feldspar and quartz crystals that form the bulk of these granitic rocks, individual uranium-238 atoms wait in their crystalline cages, some having already completed their 4.5 billion year journey to lead 206 others just beginning the radioactive countdown that will outlast the erosion of the mountain range itself. The concentration mechanisms that create uranium-rich granites operate through the physics of magmatic differentiation, where incompatible elements like uranium and thorium become progressively enriched in residual melts as more compatible elements crystallize into early forming mineral phases. This process can concentrate uranium from typical mantle abundances of about 20 parts per billion to granitic concentrations of several parts per million increases of more than 100-fold that reflect millions of years of crustal melting and remelting events. Accessory minerals within granitic rocks, tiny crystals of zircon, monazite, and apatite that constitute less than 1% of the rock volume often contain the highest concentrations of radioactive elements. A single zircon crystal smaller than a grain of sand may contain uranium concentrations exceeding several thousand parts per million, making these microscopic minerals some of the most radioactive substances found in nature. Each zircon acts as a miniature nuclear reactor, generating heat through alpha decay while simultaneously recording the age and thermal history of its host granite through the accumulation of radiogenic lead isotopes. The heat generated by radioactive decay in granitic rocks follows mathematical relationships that allow geophysicists to calculate temperature profiles throughout the continental crust with remarkable precision. The exponential decrease of radioactive element concentrations with depth, combined with the steady heat production from uranium, thorium, and potassium decay, creates characteristic geothermal gradients that increase temperature by about 25 degrees Celsius for every kilometer of depth in typical granitic terrains. Laboratory measurements of heat production in granite samples reveal the direct connection between radioactive element concentrations and thermal output. A typical granite containing 4 parts per million uranium, 15 parts per million thorium, and 4% potassium generates approximately 2 to 3 microwatts of heat per kilogram of rock through radioactive decay. When integrated over the volumes of major granite batholiths, this seemingly modest heat production becomes sufficient to drive significant thermal and chemical processes in the deep continental crust. The mystery surrounding granite-hosted radioactive heating centers on the three-dimensional distribution of uranium and thorium at depths beyond the reach of direct sampling. Drill holes and mine shafts provide access to only the uppermost portions of granite bodies, leaving the deep structure and radioactive inventory of most batholiths largely unknown. Geophysical surveys using gravity, magnetic, and electromagnetic methods can map the gross structure of granite plutons, but cannot resolve the detailed distribution of radioactive elements that controls heat production patterns. Metamorphic aureoles zones of altered rock surrounding granite intrusions preserve evidence of the thermal effects produced by radioactive heating over geological time. These aureoles often extend several kilometers into the surrounding country rock, indicating that granite bodies have maintained elevated temperatures for millions of years after their initial emplacement. The mineral assemblages developed in these contact zones reflect not only the initial heat of magmatic intrusion, but also the sustained thermal input from ongoing radioactive decay. Groundwater circulation systems in granite terrains create efficient mechanisms for extracting and redistributing radioactive heat from deep source regions. Where fracture networks allow water to penetrate to depths of several kilometers, hydrothermal convection can transport heat from radioactive granite bodies to the surface much more efficiently than conductive heat transfer through solid rock. Hot springs emerging from granite terrains often show elevated concentrations of radon and other radioactive decay products, providing direct evidence of uranium and thorium decay at depth. The age relationships of granite emplacement reveal how radioactive heating has influenced continental evolution over billions of years. Archean granite greenstone terrains, formed more than 2.5 billion years ago when Earth's radioactive inventory was significantly higher, show evidence of much more vigorous thermal activity than younger granitic provinces. The higher heat production rates in early Earth history may have facilitated the formation of the first stable continental nuclei by providing the thermal energy necessary to partially melt and differentiate the primitive crust. Uranium ore deposits associated with granitic rocks form through processes that concentrate radioactive elements from average crustal abundances to economically viable grades. These concentration mechanisms often involve hydrothermal fluids that leach uranium and thorium from granite source rocks and precipitate them in favorable structural or chemical environments. The formation of these ore deposits represents a kind of geological distillation, where millions of years of fluid circulation extract and concentrate the radioactive inventory of entire granite bodies into much smaller, high-grade deposits. The irony of granite's role as Earth's nuclear fuel storage system encompasses both temporal and chemical scales that span the entire history of the continental crust. The same granitic rocks that provide the stable foundation for human civilization contain radioactive elements in concentrations that would require careful handling if encountered in industrial settings, yet pose no hazard in their natural crystalline environment. Only took 4 billion years for stellar nucleosynthesis to become architectural stone. The uranium and thorium locked in granite buildings and monuments continue their radioactive decay at the same rate they followed when buried miles below ground. Yet the change from deep crustal environment to surface exposure alters their heat production effects from geological significance to complete irrelevance. And perhaps most elegantly paradoxical of all granite, valued throughout human history for its durability and resistance to weathering, owes much of its longevity to the very radioactive processes that will eventually transform every uranium and thorium atom it contains into stable, non-heat-producing isotopes. Radiometric dating of granite samples using uranium lead and thorium lead decay systems allows geologists to determine the age of granite emplacement with precisions of less than 1%. These dating techniques rely on the same radioactive decay processes that generate heat in granite bodies, creating a direct connection between the nuclear processes that warm the deep crust and the geochronological methods used to understand crustal evolution. The warmth continues to emanate from granite bodies scattered throughout the continental crust, each pluton representing a concentrated reservoir of nuclear fuel that has been burning steadily for tens to hundreds of millions of years. In the deep mines that penetrate granite bodies, geologists measure rock temperatures that reflect the cumulative heat production from countless radioactive decay events occurring in crystals that formed when dinosaurs ruled the Earth or when the first complex cells were evolving in ancient seas. Somewhere in the feldspar crystals of every granite outcrop, in the zircon grains embedded in granitic gneisses formed billions of years ago, in the uranium-bearing minerals scattered through the deepest parts of continental batholiths, radioactive atoms continue their patient countdown toward stability while warming the crystalline matrix that holds them in place. The granite holds its nuclear fire like a geological battery, storing the energy released by stellar death and converting it grain by grain into the gentle heat that maintains the thermal structure of the continental crust. The granite holds the warmth, crystal by crystal, decay by decay, in the endless patience of plutonic time. Along the mid-ocean ridges where tectonic plates separate at the speed of growing hair, radioactive heat drives the most systematic and geometrically precise manifestation of Earth's internal nuclear engine. Here, beneath 2 miles of seawater and beyond the reach of sunlight, mantle rock heated by 4 billion years of uranium, thorium, and potassium decay rises toward the seafloor and spreads outward in both directions, creating new oceanic crust with the mechanical regularity of a planetary assembly line. The mid-Atlantic ridge, snaking down the center of the Atlantic Ocean like a 20,000-mile-long zipper, marks where the heat accumulated from radioactive decay in the underlying mantle drives the separation of the American and European African plate systems. Every year, this ridge system produces roughly 20 cubic kilometers of new basaltic crust, each cubic meter containing the chemical signature of radioactive processes that have been operating in mantle source regions for billions of years. The potassium, uranium, and thorium carried in these fresh basalts represent samples of the deep Earth's nuclear inventory, brought to the surface through melting processes driven by the very radioactive heat these elements have been generating. The geometry of seafloor spreading follows mathematical relationships that reflect the underlying physics of thermal convection and viscous flow in the mantle. As radioactive heat warms mantle rock beneath ridge systems, thermal expansion reduces the density of the heated material, creating buoyancy forces that drive upward flow at rates of a few centimeters per year. This ascending mantle rock undergoes decompression melting as it rises, generating basaltic magmas that fill the gap created by the diverging plates above. Basaltic pillow lavas erupted at mid-ocean ridges preserve the thermal signature of their radioactive heat sources in both their major element chemistry and their trace element patterns. The degree of partial melting that produces mid-ocean ridge basalts depends critically on the temperature of the upwelling mantle, which in turn reflects the integrated heat production from radioactive decay over millions of years. Variations in ridge basalt chemistry along the global ridge system provide maps of mantle temperature variations that ultimately trace back to differences in radioactive element distributions in the deep Earth. Hydrothermal vent systems at mid-ocean ridges create dramatic expressions of the heat flow driven by radioactive processes in the underlying mantle. Black smoke events, where superheated water emerges at temperatures exceeding 350 degrees Celsius, represent the surface manifestation of circulation systems that extract heat from newly formed oceanic crust and transport it directly to the seafloor. The heat that drives these circulation systems originates as radioactive decay in mantle source regions hundreds of kilometers below the ridge axis. The spreading rate of mid-ocean ridges correlates with the vigor of the underlying mantle convection, which depends on the thermal structure maintained by radioactive heating. Fast-spreading ridges like the East Pacific Rise, where plates separate at rates exceeding 10 centimeters per year, typically overlie regions of vigorous mantle upwelling, driven by elevated temperatures maintained through radioactive heat production. Slow-spreading ridges show more subdued thermal signatures, reflecting either lower radioactive heat production in their mantle sources or more efficient heat loss through conductive cooling. Laboratory experiments designed to understand ridge processes use high-pressure apparatus to melt mantle rock samples under conditions that simulate the decompression experienced by upwelling mantle beneath mid-ocean ridges. These experiments reveal that small changes in mantle temperature, potentially reflecting variations in radioactive heat production, can significantly affect both the volume of melt produced and the depth at which melting begins. A temperature increase of just 50 degrees Celsius in the upwelling mantle can double the fraction of melt produced during decompression. The mystery surrounding mid-ocean ridge magmatism centers on the three-dimensional structure of melt delivery systems beneath ridge axes. Seismic imaging suggests that melts generated over broad regions of upwelling mantle areas, potentially hundreds of kilometers wide, must be focused into narrow zones of magma delivery only a few kilometers wide at ridge axes. This focusing process may involve complex interactions between thermal structure, mantle flow patterns, and the distribution of radioactive heat sources in the upwelling material. Transform faults that offset ridge segments create natural laboratories for studying the relationship between radioactive heating and ridge processes, where transform faults expose deep sections of oceanic crust through tectonic unroofing. Geologists can sample the complete sequence from seafloor basalts through the underlying gabbroic rocks that crystallized in sub-ridge magma chambers. These exposed sections preserve records of the thermal conditions during crustal formation, including evidence of the radioactive heat sources that maintained magma chambers in their molten state. The isotopic signatures of mid-ocean ridge basalts provide direct evidence of radioactive decay processes in mantle source regions. Ratios of radiogenic isotopes, daughter products of uranium, thorium, and potassium decay vary systematically along ridge systems, reflecting the time-integrated effects of radioactive heating in different portions of the mantle. These isotopic variations create maps of mantle evolution that extend back billions of years, recording how radioactive elements have been distributed and redistributed throughout Earth's interior. Magnetic anomaly patterns preserved in oceanic crust provide an independent record of spreading rates and ridge behavior extending back more than 100 million years. The consistency of these patterns suggests that the radioactive heat sources driving mantle convection and ridge spreading have maintained relatively stable output over time periods much longer than human civilization. This stability reflects the extremely long half-lives of the major heat-producing isotopes, particularly uranium-238 and thorium-232. The irony of seafloor spreading encompasses both the permanence of the driving forces and the ephemeral nature of the oceanic crust they create. The same radioactive processes that have been operating for 4 billion years drive the creation of oceanic crust that survives at Earth's surface for at most 200 million years before being recycled back into the mantle through subduction processes. Only took 4 billion years for stellar nucleosynthesis to become oceanic recycling. The heat that drives ridge spreading ultimately derives from nuclear reactions in mantle source regions that may take millions of years to reach the surface, yet creates oceanic crust that begins cooling and contracting the moment it forms. And perhaps most geometrically elegant of all the linear ridge systems that appear as simple cracks in the seafloor represent the two-dimensional surface expression of three-dimensional convection cells that extend hundreds of kilometers into the mantle and operate over time scales spanning millions of years. Drilling programs designed to penetrate the entire thickness of oceanic crust have revealed the detailed architecture of ridge crest magmatic systems. The upper oceanic crust consists of pilobasalts and massive flows that erupted directly onto the seafloor, underlain by a complex of vertical dikes that fed these surface eruptions. Beneath the dike complex lies a layer of slowly cooled gabbroic rocks that crystallized in magma chambers maintained in their molten state by the steady input of radioactive heat from below. The spreading continues along the global network of mid-ocean ridges, driven by thermal energy that originates as radioactive decay in uranium, thorium, and potassium atoms scattered throughout the mantle. The process operates with the precision of atomic clockwork scaled up to planetary dimensions, creating new seafloor at predictable rates while consuming mantle material that has been heated by nuclear processes operating since Earth's formation. Somewhere beneath every segment of the global ridge system, mantle rock warmed by billions of radioactive decay events rises toward the surface, melts, and erupts to create basaltic crust that immediately begins its journey toward distant continents. The ocean floors spread outward from these ridge axes like conveyor belts, carrying the thermal and chemical signature of Earth's nuclear interior towards subduction zones, where the cycle of heating, melting, and renewal will begin again. The ocean floors spread wide, ridge by ridge, eruption by eruption, in the endless patience of spreading time, where the radioactive fire burning deep within Earth's crust finds pathways to the surface through networks of fractures and permeable rock. Hot springs emerge as gentle messengers of the nuclear processes occurring miles below. These thermal features, scattered across every continent and ranging from barely warm seeps to violently boiling geysers, represent the direct intersection of groundwater circulation systems, with heat sources maintained by billions of years of uranium, thorium, and potassium decay in the underlying bedrock. Yellowstone's Grand Prismatic Spring, the largest hot spring in the United States and third largest in the world, draws its heat from a vast magma chamber that lies several miles beneath the Yellowstone Plateau. This magma chamber, estimated to contain more than 15,000 cubic miles of partially molten rock, maintains its elevated temperature through the steady input of radioactive heat from uranium and thorium decay in both the magma itself and the surrounding granitic crust. The spring's surface temperature of approximately 70 degrees Celsius represents the culmination of a thermal journey that began with atomic decay in radioactive elements buried at depths where pressure exceeds 1,000 times atmospheric pressure. The hydrothermal circulation systems that feed hot springs operate through convection cells that can extend several kilometers into the Earth's crust. Cold groundwater descends through fracture networks and permeable rock formations, gradually warming as it encounters the elevated temperatures maintained by radioactive heating at depth. As this water heats up, it becomes less dense and begins to rise through different pathways, eventually emerging at the surface as hot springs or geysers. The entire circulation process can take decades to centuries, during which the water serves as a thermal transport medium, carrying heat from radioactive sources to the surface. The chemistry of hot spring waters provides direct evidence of interaction with radioactive source rocks at depth. Many hot springs show elevated concentrations of radon-222, a radioactive gas produced by the decay of uranium-238 in granitic bedrock. The presence of radon in hot spring gases indicates that these waters have been in contact with uranium-bearing rocks for sufficient time to allow radon gas to accumulate and be transported to the surface. Some hot springs contain radon concentrations hundreds of times higher than typical groundwater, reflecting intense interaction with radioactive source rocks. Geothermal gradients measured in the vicinity of hot springs often exceed normal crustal values by factors of 2 to 10, indicating the presence of elevated heat sources at relatively shallow depths. These enhanced geothermal gradients reflect the combined effects of radioactive heat production in underlying granitic rocks and the efficient heat transport provided by circulating groundwater. In some geothermal systems, the measured heat flow approaches values typical of active volcanic regions, despite the absence of recent volcanic activity. The distribution of hot springs around the world shows statistical correlations with the underlying geology, particularly with the presence of uranium and thorium-rich granitic rocks at depth. The western United States, with its abundance of tertiary granite intrusions containing elevated concentrations of radioactive elements, hosts thousands of hot springs ranging from small seeps to major geothermal systems capable of generating electricity. Similar correlations exist in other regions of the world where granitic terrains provide both radioactive heat sources and the fracture networks necessary for deep groundwater circulation. Laboratory analysis of mineral precipitates from hot springs reveals the long-term effects of water-rock interaction in radioactively heated systems. Travertine deposits formed by calcium carbonate precipitation from hot spring waters often contain elevated concentrations of uranium and thorium, indicating that these radioactive elements are being actively leached from source rocks and transported in the circulating groundwater. Some hot spring deposits contain uranium concentrations approaching ore grade, representing the surface expression of hydrothermal concentration processes operating at depth. The timing of hot spring activity often correlates with regional tectonic events that affect groundwater circulation patterns or alter the pathways for heat transport from radioactive sources. Earthquakes can dramatically increase or decrease the flow rate of hot springs by opening new fractures or closing existing ones, demonstrating the close connection between structural geology and hydrothermal processes. Some hot springs show seasonal variations in temperature and flow rate that reflect changes in the regional groundwater circulation driven by precipitation patterns and surface hydrology. The mystery surrounding hot spring systems centers on the detailed mechanisms of heat and mass transport in fractured rock environments. Computer models of hydrothermal circulation require precise knowledge of fracture network geometry, permeability distributions, and heat source locations to accurately predict hot spring behavior. Most of these parameters cannot be directly measured, particularly at the depths where radioactive heating is most significant, forcing scientists to infer subsurface conditions from surface observations and limited drilling data. Isotopic studies of hot spring waters provide insights into the sources and residence times of the fluids feeding these thermal features. Oxygen and hydrogen isotope ratios indicate that most hot spring waters originated as meteoric precipitation, rainwater, or snowmelt that has circulated through deep groundwater systems for extended periods. Carbon isotope ratios in dissolved carbon dioxide often show evidence of interaction with carbonate rocks or organic matter at depth, while helium isotope ratios can indicate the degree of interaction with radioactive source rocks containing uranium and thorium. Geothermal energy systems harness the heat flow from radioactive sources to generate electricity and provide direct heating applications. The Geysers geothermal field in California, the world's largest geothermal complex, produces electricity from steam heated by radioactive decay in underlying granitic rocks of the Clear Lake volcanic field. Iceland's extensive geothermal energy infrastructure exploits heat from both radioactive sources in the continental crust and elevated mantle temperatures associated with the Mid-Atlantic Ridge System. The irony of hot springs encompasses both their role as natural expressions of nuclear processes and their cultural significance as symbols of natural tranquility. The same radioactive decay that powers nuclear reactors and atomic weapons provides the gentle heat that creates the world's most peaceful and meditative natural environments. Only took 4 billion years for stellar nucleosynthesis to become spa therapy. Hot springs that have been sites of human healing and spiritual practice for thousands of years derive their therapeutic warmth from the same nuclear reactions that occur in weapons facilities and power plants. And perhaps most quietly paradoxical of all the radioactive elements that make some hot spring waters mildly hazardous for extended exposure also provide the energy necessary to drive the circulation systems that dilute these same elements to safe concentrations through mixing with meteoric groundwater. Microbiological studies of hot springs have revealed diverse ecosystems of thermophilic organisms that thrive in environments heated by radioactive decay. These organisms, some capable of surviving temperatures exceeding 80 degrees Celsius, represent some of Earth's most ancient life forms and provide insights into the conditions under which life may have first evolved. The metabolic pathways used by these organisms often involve chemical reactions with minerals that have been altered by long-term exposure to radioactive heating and hydrothermal circulation. Monitoring networks at major geothermal systems track the long-term evolution of hot spring behavior as radioactive heat sources gradually diminish through radioactive decay. Over human timescales, these changes are barely detectable, but geological evidence suggests that some hot spring systems have been active for millions of years, sustained by the extremely long half-lives of uranium-238 and thorium-232. Other hot spring systems show evidence of episodic activity related to changes in groundwater circulation patterns or heat source intensity. The springs continue to emerge from fractures and permeable zones throughout the world's continental crust, each one representing a unique pathway for radioactive heat to reach the surface through interaction with circulating groundwater systems. From the silica-depositing geysers of Yellowstone to the carbonate-precipitating springs of Travertine terraces, each thermal feature reflects the specific geological conditions that allow radioactive heat to be captured and transported by groundwater circulation. Somewhere beneath every hot spring, radioactive atoms continue their ancient decay cycles, while groundwater circulation systems extract and transport their thermal energy toward the surface. The hot springs mark the locations where the patient nuclear fire of the deep crust intersects with the hydrologic cycle, creating oases of warmth that connect the atomic scale of radioactive decay to the human scale of therapeutic soaking and geothermal energy production. The hot springs mark the surface, seep by seep, thermal feature by thermal feature, in the endless patience of hydrothermal time. In the deepest reaches of geological time, where million-year intervals pass like seasons and billion-year epochs mark the major chapters of Earth's thermal history, the radioactive elements that power the planet's internal engine follow decay schedules that operate according to the fundamental constants of nuclear physics. These half-lives, the time required for half of any population of radioactive atoms to complete their transformation, represent some of the most precisely known and unchangeable quantities in all of science. Yet their implications for planetary evolution unfold over timescales so vast that human consciousness can barely grasp their significance. Uranium-238, the most abundant of Earth's heat-producing isotopes, follows a half-life of 468 billion years, a duration so close to Earth's own age that roughly half of the uranium present at the planet's formation has already completed its decay to lead-206. This means that early in Earth's history, when the first continental crust was solidifying and the earliest life forms were emerging in ancient seas, the planet's uranium inventory was nearly double what it is today. The thermal consequences of this higher radioactive heat production may have been profound, potentially driving more vigorous mantle convection, more rapid plate tectonic processes, and higher rates of volcanism than anything observed in the modern geological record. Thorium-232, with its even longer half-life of 14.05 billion years, operates on timescales that exceed the current age of the universe. Most thorium atoms present in Earth today have been waiting in their crystalline prisons since before the solar system formed, and will continue their radioactive countdown for billions of years after the sun has exhausted its nuclear fuel and begun its transformation into a white dwarf star. The thorium atoms decaying today in granite bedrock beneath mountain ranges began their existence in the nuclear furnaces of stars that lived and died before Earth's accretion from the solar nebula. Potassium-40, with its comparatively rapid half-life of 1.25 billion years, has undergone more than 3 complete half-life cycles since Earth's formation. This means that only about 1/8 of the original potassium-40 inventory remains, with the rest having decayed to argon-40 and calcium-40 through the various pathways of radioactive transformation. The heat production from potassium-40 was therefore much higher in the Archean eon, when this isotope may have provided the dominant source of radioactive heating for mantle convection and early crustal differentiation processes. The mathematics of exponential decay create fascinating temporal overlaps between different radioactive systems. While uranium-238 atoms are completing their first half-life cycle since Earth's formation, thorium-232 atoms are only beginning their radioactive journey. Meanwhile, multiple generations of shorter-lived isotopes have come and gone completely, their decay products now serving as the daughter isotopes that geologists use for radiometric dating of ancient rocks. Each radioactive system operates according to its own temporal rhythm, yet all contribute to the integrated heat budget that drives geological processes. Computer models of Earth's thermal evolution must account for the changing radioactive heat production over geological time. These models suggest that total radioactive heat production may have been 3 to 4 times higher in the Archean eon than it is today, potentially explaining the formation of early continental crust through processes that no longer operate with the same intensity. The gradual decline in radioactive heating over Earth's history represents a kind of planetary cooling that operates independently of other thermal processes like the cooling of primordial accretional heat. Laboratory measurements of decay constants for uranium, thorium, and potassium isotopes represent some of the most precise determinations in all of nuclear physics. These measurements, carried out using mass spectrometers and radiation counting systems, can determine half-lives with uncertainties of less than 0.1%. The consistency of these measurements across different laboratories and measurement techniques provides confidence that radioactive decay rates have remained constant throughout Earth's history, despite the extreme conditions of temperature and pressure in the deep interior. The mystery surrounding deep-time radioactive processes centers on the initial distribution of radioactive elements in the early solar system and their subsequent concentration into planetary bodies. Current models suggest that uranium, thorium, and potassium formed through nucleosynthesis processes in supernova explosions and asymptotic giant branch stars that occurred billions of years before the solar nebula condensed. The specific mechanisms that concentrated these elements into rocky planets like Earth, while leaving gas giants relatively depleted, remain active areas of cosmochemical research. Meteorite studies provide constraints on the abundance and isotopic composition of radioactive elements in the early solar system. Chondritic meteorites, which represent relatively unaltered samples of solar nebula material, contain uranium, thorium, and potassium in ratios that allow scientists to estimate the initial inventory of these elements in Earth and other terrestrial planets. The heat production calculated from these abundances helps explain the thermal evolution of planetary interiors over billion-year timescales. The geological record preserves evidence of the higher radioactive heat production that characterized Earth's early history. Archean volcanic rocks often show chemical signatures indicative of higher mantle temperatures, while the widespread development of granite greenstone terrains in rocks older than 2.5 billion years may reflect the more vigorous crustal melting processes driven by elevated radioactive heating. Some researchers suggest that the transition from Archean-style tectonics to modern plate tectonic processes reflects the gradual decline in radioactive heat production as uranium and potassium inventories diminished through radioactive decay. Isotopic studies of ancient rocks reveal the long-term effects of radioactive decay on Earth's chemical evolution. The accumulation of radiogenic lead isotopes from uranium decay, radiogenic strontium from rubidium decay, and radiogenic argon from potassium decay creates isotopic signatures that record billions of years of radioactive processes. These signatures allow geologists to trace the movement of radioactive elements through different reservoirs in Earth's interior and to constrain the timing of major differentiation events in Earth's history. The irony of deep-time radioactive processes encompasses both the precision of nuclear physics and the uncertainty of geological extrapolation. While decay constants can be measured with extraordinary accuracy in laboratory settings, their integration over planetary scales and geological time periods involves assumptions about processes that cannot be directly observed. Only took 4 billion years for stellar nucleosynthesis to become geochronological uncertainty. The same radioactive processes that provide the most reliable methods for dating ancient rocks also represent continuously changing heat sources that make modeling Earth's thermal evolution inherently complex. And perhaps most profoundly paradoxical of all the radioactive elements that power geological processes over billions of years are themselves gradually disappearing through the very decay processes they enable, ensuring that Earth's thermal future will be fundamentally different from its thermal past. Future projections of Earth's radioactive heat budget suggest that total heat production will continue to decline gradually over the next billion years. Uranium-238 will complete another significant fraction of its decay. Potassium-40 will become essentially extinct, and even the extremely long-lived thorium-232 will show measurable decreases in abundance. These changes will gradually reduce the vigor of mantle convection, potentially leading to the eventual cessation of plate tectonic processes and the transition to a more Venus-like thermal regime. The deep time burn continues in radioactive atoms scattered throughout Earth's interior, each isotope following its predetermined decay schedule while contributing to heat production patterns that have been evolving since the planet's formation. The uranium atoms that will decay tomorrow began their countdown billions of years ago, while other uranium atoms present today may continue waiting for billions of years more before completing their transformation to stable lead isotopes. Somewhere in the crystal matrices of ancient rocks, in the flowing mineral assemblages of the mantle, in the thermal reservoirs that power volcanic systems and drive plate tectonic processes, radioactive elements continue their patient transformation according to the unchangeable laws of nuclear physics. The deep time burn connects the formation of heavy elements in dying stars to the geological processes that shape Earth's surface, operating over timescales that span the entire history of the universe while following quantum mechanical principles that govern individual atomic nuclei. The deep time burn continues, half-life by half-life, decay by decay, in the endless patience of nuclear time. Across the vast expanses of geological time, the continents have wandered Earth's surface like massive ships on a slow-motion ocean, their journeys powered by the patient heat of radioactive decay in the underlying mantle and deep crust. This continental drift operates at speeds measured in centimeters per year, roughly the rate at which human fingernails grow, yet over hundreds of millions of years. These imperceptible movements have carried land masses across thousands of miles of planetary surface, assembling and breaking apart supercontinents in cycles that reflect the deep thermal rhythms driven by nuclear fire below. Pangaea, the supercontinent that began breaking apart roughly 200 million years ago, represents one of the most recent expressions of the thermal forces generated by radioactive heating in Earth's interior. The rifting processes that split this vast landmass into the Atlantic Ocean began when radioactive heat accumulated beneath the continental lithosphere, warming the underlying mantle until thermal expansion and buoyancy forces overcame the mechanical strength of the overlying rocks. The energy required to crack a continent and create new ocean basins ultimately derives from the patient accumulation of heat from uranium, thorium, and potassium decay over tens of millions of years. The geological record preserves evidence of even more ancient continental assemblages, supercontinents that formed and dispersed according to thermal cycles driven by the changing distribution of radioactive heat sources in Earth's interior. Rodinia assembled roughly 1 billion years ago, and even earlier, supercontinents inferred from paleomagnetic and geological evidence reflect the operation of thermal processes that have been reshaping Earth's surface for billions of years. Each assembly and breakup cycle represents a different phase in the planet's thermal evolution, influenced by the gradual decline in radioactive heat production as uranium and potassium inventories diminish through radioactive decay. The mechanism of continental drift operates through the physics of thermal convection in the mantle, where radioactive heating creates density differences that drive large-scale circulation patterns. Hot mantle rock, warmed by radioactive decay, rises beneath continents and spreads laterally as it approaches the surface, exerting drag forces on the overlying lithosphere that can gradually move entire continents across Earth's surface. These convection currents operate like vast underground rivers of flowing rock, carrying heat from radioactive source regions deep in the mantle to shallow depths where they influence surface geology. Hotspot tracks chains of volcanic islands and seamounts created as tectonic plates move over stationary mantle. Plumes provide some of the most direct evidence for continental motion driven by radioactive heating. The Hawaiian Emperor Seamount Chain, extending for more than 3,000 miles across the Pacific Ocean floor, records the northwestward motion of the Pacific Plate over a hotspot that may be sustained by radioactive heating in a deep mantle plume. The age progression of volcanic rocks along this chain documents plate motion over the past 70 million years with remarkable precision. Computer models of mantle convection reveal how radioactive heating patterns influence the trajectories of continental drift over geological time. Regions of elevated uranium and thorium concentration in the deep mantle create preferential sites for the initiation of mantle plumes, while the overall distribution of radioactive elements affects the wavelength and intensity of convection cells that drive plate motion. Small changes in radioactive heat production can alter continental drift rates by factors of 2 or more, explaining some of the variations in tectonic activity observed in the geological record. The relationship between continental drift and radioactive heating creates feedback systems that influence the long-term evolution of both processes. As continents move over regions of varying radioactive heat production, they experience different thermal regimes that affect their internal structure and stability. Continental lithosphere that passes over uranium-rich portions of the mantle may undergo partial melting and crustal recycling, while regions that traverse thorium-depleted areas may cool and thicken through conductive heat loss. Paleomagnetic studies of ancient rocks provide quantitative records of continental motion extending back billions of years. These studies reveal that continental drift rates have varied significantly over geological time, with periods of rapid motion alternating with intervals of relative stability. Some of these variations correlate with changes in global volcanic activity and other indicators of mantle thermal state, suggesting that the vigor of radioactive heating has influenced continental drift throughout Earth's history. The assembly of supercontinents appears to follow cyclical patterns with periodicities of roughly 400 to 600 million years. Timescales that may reflect the thermal time constants for heat accumulation and dissipation in the deep mantle. During supercontinent assembly, radioactive heat becomes trapped beneath large continental masses, leading to elevated mantle temperatures that eventually drive rifting and breakup. The dispersal phase allows heat to escape more efficiently through ocean ridge systems, leading to mantle cooling that favors the next phase of continental assembly. Isotopic studies of ancient rocks reveal how continental drift has redistributed radioactive elements over geological time. Uranium, thorium, and potassium tend to be concentrated in continental crust relative to oceanic crust, meaning that continental drift represents a mechanism for transporting Earth's nuclear fuel inventory across the planetary surface. The collision and suturing of continents during supercontinent assembly create zones of doubled crustal thickness with correspondingly high concentrations of radioactive elements. The mystery surrounding continental drift centers on the detailed mechanisms that initiate continental rifting and the factors that determine where new ocean basins will form. While the general physics of thermal convection and radioactive heating are well understood, the specific conditions that cause continents to break apart at particular locations and times remain difficult to predict. The heterogeneous distribution of radioactive elements in the continental crust and underlying mantle creates complex thermal patterns that make continental rifting a fundamentally chaotic process over long time scales. Laboratory experiments using scaled physical models demonstrate how thermal convection driven by differential heating can produce continental drift-like motions in viscous fluids. These experiments reveal that the pattern and rate of convection depend critically on the spatial distribution of heat sources, with concentrated heating creating narrow upwelling plumes, while distributed heating tends to produce broader, more stable convection cells. The implications for real continental drift depend on how radioactive elements are distributed in Earth's mantle, a question that remains largely unanswered due to the inaccessibility of deep mantle source regions. The irony of continental drift encompasses both the enormous energy required to move entire continents and the gentle, persistent nature of the radioactive processes that provide this energy. The heat released by a single uranium atom undergoing alpha decay, barely enough energy to lift a grain of dust, becomes, when multiplied across billions of atoms and integrated over millions of years, sufficient to crack continents and create ocean basins thousands of miles wide. Only took 4 billion years for stellar nucleosynthesis to become continental demolition. The same radioactive elements that create stable, long-lived continental crust also provide the energy necessary to break that crust apart and redistribute it across Earth's surface. And perhaps most geographically paradoxical of all the continents that appear most permanent and unchanging from human perspectives are actually in constant motion, carried along by thermal currents driven by nuclear reactions occurring hundreds of miles below their foundations. Geodetic measurements using satellite positioning systems can now detect continental drift in real time, measuring the centimeter-per-year motions that reflect radioactive heating in the deep Earth. These measurements reveal that continental drift continues today at rates comparable to those inferred from the geological record, confirming that radioactive heat production remains sufficient to drive large-scale tectonic processes despite the gradual decline in uranium and potassium inventories over geological time. The drift continues across every ocean basin, where mid-ocean ridge systems mark the boundaries between diverging continental masses and transform faults, accommodate the complex geometry of motion on a spherical planet. Subduction zones around the Pacific Ring of Fire consume oceanic crust created at spreading centers, completing the convection cells that redistribute both heat and matter throughout Earth's interior. Somewhere beneath every continent, thermal currents driven by radioactive decay continue to exert the forces that move land masses across Earth's surface at speeds imperceptible to human senses, but dramatic over geological time. The continental drift connects the nuclear physics of radioactive decay to the largest scale geological processes, ensuring that the patient energy released by atomic transformations continues to reshape the planetary surface in ways that will persist for billions of years. The continental drift continues, centimeter by centimeter, continent by continent, in the endless patience of tectonic time. In the distant future, when the sun has swollen into a red giant and Earth's oceans have long since boiled away into space, the last reserves of uranium-238 will still be undergoing radioactive decay in whatever remains of the planet's interior. But this future lies so far ahead that it challenges human comprehension billions of years hence, when the radioactive fuel that has powered geological processes since Earth's formation will finally approach exhaustion. The cooling that will come represents not a sudden shutdown, but a gradual dimming of the nuclear fire that has burned in planetary darkness for longer than complex life has existed. The mathematics of radioactive decay ensure that Earth's thermal future follows predictable patterns governed by the half-lives of uranium, thorium, and potassium isotopes. In 1 billion years, a span of time equal to the period since the first complex cells evolved roughly half of the remaining uranium, 238 will have completed its transformation to lead-206, reducing the planet's nuclear heat production by another significant increment. Potassium-40, with its shorter half-life, will have undergone another complete decay cycle, leaving only 1/16 of today's inventory still radioactive. Computer models of Earth's thermal evolution project that total radioactive heat production will decline by approximately 30% over the next billion years, falling to levels that may no longer sustain the vigorous mantle convection necessary for plate tectonic processes. The transition from an active, dynamic planet to a more thermally stable, geologically quiescent world may occur gradually over hundreds of millions of years, as declining heat production reduces the temperature differences that drive convection in the mantle. Thorium-232, with its extraordinarily long half-life of 14 billion years, will continue providing substantial heat production long after uranium and potassium have largely decayed away. In the very distant future, thorium may become Earth's dominant radioactive heat source, sustaining reduced levels of geological activity through time periods that exceed the current age of the universe. The thorium atoms decaying in that far future will be the same atoms present in Earth's crust today, having waited through the entire history of complex life, human civilization, and whatever comes after. The geological consequences of declining radioactive heat production will unfold over timescales that dwarf human history. As mantle temperatures decrease, the vigor of convection will diminish, leading to slower rates of seafloor spreading, reduced volcanic activity, and eventually the cessation of plate tectonic processes altogether. Continental drift, which has operated continuously for billions of years, may gradually slow and finally stop as the thermal engine that drives it runs out of nuclear fuel. Laboratory studies of mantle convection under reduced heating conditions suggest that Earth's transition to thermal quiescence will not be uniform or predictable. Computer simulations indicate that mantle convection may become increasingly sluggish and episodic as radioactive heat production declines, with periods of relative stability punctuated by sudden reorganizations of convection patterns. These thermal instabilities could produce brief episodes of intense geological activity separated by long periods of dormancy. The mystery surrounding Earth's thermal future centers on the complex interactions between different heat sources and heat loss mechanisms as radioactive production declines. While radioactive decay provides roughly half of Earth's current heat budget, the remainder comes from the slow cooling of primordial heat trapped during the planet's formation. The relative importance of these different heat sources will change as radioactive elements decay away, potentially leading to thermal evolution patterns that differ significantly from current models. Comparative planetary studies provide insights into the thermal fate of rocky worlds as their radioactive fuel supplies diminish. Mars, with its smaller size and presumably lower initial inventory of radioactive elements, may represent an example of what Earth could become in the distant future, a geologically inactive world where surface processes are dominated by impact cratering and atmospheric evolution rather than internal heat-driven tectonics. The transition to reduced geological activity will affect not only large-scale processes like plate tectonics, but also the smaller-scale phenomena that make Earth habitable for life as we know it. Hydrothermal circulation systems driven by radioactive heating in the deep crust may gradually weaken and eventually cease, eliminating the hot springs and geothermal vents that currently support diverse ecosystems. The magnetic field generated by convection in Earth's liquid outer core may also weaken as core temperatures decline, potentially exposing the planet's surface to increased cosmic radiation. Isotopic studies of ancient rocks provide perspectives on how declining radioactive heat production has already influenced Earth's evolution over the past 4 billion years. The transition from Archean-style geology, characterized by widespread granite greenstone terrains and apparent high mantle temperatures, to modern plate tectonic processes may reflect the gradual decline in radioactive heating as uranium and potassium inventories diminished through decay. The irony of Earth's thermal future encompasses both the inevitability of cooling and the extraordinary timescales over which this cooling will occur. The nuclear fuel that has powered geological processes since before life evolved will eventually be exhausted, yet this exhaustion will take longer to complete than life has existed on Earth. Only took 4 billion years for stellar nucleosynthesis to become planetary retirement planning. The same radioactive processes that make Earth geologically active today guarantee that it will become geologically inactive in the future, creating a kind of built-in obsolescence for the dynamic processes that shape the planetary surface. And perhaps most poignantly paradoxical of all, the cooling of Earth's interior will occur so gradually that countless generations of future life forms, if they exist, will never notice the change, experiencing what appears to be a stable, unchanging world, even as it slowly loses the internal fire that has sustained it for billions of years. Long-term climate models must account for the gradual reduction in volcanic outgassing and hydrothermal activity as radioactive heating declines. These processes currently play important roles in regulating atmospheric composition and global climate, meaning that their weakening could have significant consequences for surface conditions. The carbon cycle, which depends partly on volcanic carbon dioxide emissions and weathering processes driven by hydrothermal circulation, may undergo fundamental changes as Earth's internal heat engine gradually shuts down. Speculation about Earth's ultimate thermal fate extends to timescales that challenge scientific modeling capabilities. In 10 billion years, when the Sun begins its evolution toward becoming a white dwarf star, Earth's radioactive heat production will have declined to a small fraction of current levels. The planet may have become a geologically dead world, with a solid mantle, inactive volcanoes, and surface processes dominated entirely by external forces like solar radiation and cosmic impacts. The cooling continues in computer models and theoretical projections that extend billions of years into the future, tracking the gradual decay of Earth's nuclear fuel supplies and the corresponding decline in geological activity. Each model run represents thousands of CPU hours spent calculating how individual radioactive decay events will accumulate over geological time to produce planetary-scale changes in thermal structure and tectonic behavior. Somewhere in the crystal matrices of future rocks, in mantle minerals that will flow more slowly as temperatures decline, in the cooling cores of planets throughout the galaxy, radioactive elements will continue their patient countdown towards stability while providing diminishing amounts of heat to sustain geological processes. The cooling that will come represents the inevitable consequence of the nuclear fire that has burned since Earth's beginning, ensuring that the dynamic planet we inhabit today will gradually transform into something fundamentally different over time scales that exceed human imagination. The cooling that will come unfolds, decay by decay, half-life by half-life, in the endless patience of thermal evolution time,